the very last one that I was looking at, and this one came out, I think, last week, maybe Friday or something. There was a VLC exploit. And what I'm going to do is I'm just going to power this off just so I at least only have one machine that's.
You said you put this out there on GitHub or whatever.
Yeah, well, so this CERT Tapioca is on GitHub.
Right.
You just run the installer, and now you have a Tapioca VM. If you want to take the extra steps to turn it into a wildcard server, it's documented here. So you can just follow the steps and make your own. I took the steps just to make it, so I figured, you don't need to actually go through and build your own.
You just can put the location in the chat on V1 where it is.
Yeah. There's a directory. Yeah, I'll do that. Yeah. One of the things that I looked at recently, and we should be good. There was a VLC exploit. This was added to Metasploit, and I decided to look at it because, does it work? One of the things that I'm interested in is attackers' tradecraft for how are they able to exploit modern software to be able to achieve code execution, because the basic defenses of DEP and ASLR are pretty good. Like, it used to be that I could run some files through BFF and fuzz some things, and eventually I get the instruction pointer, and then I win because I just point it to the code I want to run. And well, it turns out modern software is a lot better. This is one of our goals for releasing our fuzzing tool, is that we wanted to increase the quality of, get rid of this low-hanging fruit of easily exploitable crashers, but then also let software developers realize that they need to step up their game and use some sorts of defenses. So at some point in time, I found a Python file that would generate an exploit for VLC. Actually, this one was added to Metasploit recently. This one's been around since June 6th, so not terribly new, but what's kind of interesting is it says that it was tested on Windows 10 x64. So being a 64-bit app, it's no magic defense, but it's an indicator that it's probably modern software. So this Python script, it does some stuff, yada yada yada. Now what's interesting in this particular case is I noticed that it has two structures here that are ROP gadgets. So I've got ROP gadgets for 64-bit, and I've got ROP gadgets for 32-bit. Are you guys familiar at all with ROP? Return-oriented programming. Basically, if I ever am able to subvert the instruction pointer of an application I'm targeting, if I can choose an interesting location for that instruction pointer to go to, I might be able to put together a chain of addresses that get it to do something interesting here. So if I look here on 64-bit VLC 228, I can see at this particular location, this is the location for Exchange ESP with EAX. This is your standard stack pivot. When you're running a program, the stack is keeping track of locations of called functions and stuff like that. Anytime I now change my stack pointer to be something drastically different or unexpected, that's a sign that something bad is happening. And this is where Emmet comes into play in Windows Defender Exploit Guard. Anytime your stack pointer changes unexpectedly, it'll kick in and say, hey, something sketchy is happening here. Well, we'll run VLC, and I'm going to run Process Explorer. And we'll get down a path that I went down, and I just finally came to an end to the path this morning. So this is actually pretty timely. In Process Explorer, you can configure your columns to display a number of things, including ASLR. ASLR is basically, does the application in question leverage address space layout randomization, meaning it'll be loaded at a different location. What do we see for VLC? What do you suppose? Do you think VLC will be randomized? See, so let me go back a little bit. I know I'm changing gears pretty quickly here. What allows people to produce ROP chains like this is predictable memory addresses. Every time I open this exploit, it will attempt to go to this location and it'll try to do a stack pivot, and then it'll do some things like popping values into the registers, and then virtual protect basically says, hey, make this code executable. And then you got your shellcode, right? The way that ASLR breaks exploits is that you can no longer predict where you need to go. Return-oriented programming, now, unless you're able to leverage a memory leak that's able to like leak where a module is loaded in memory, and it's in a dynamic language like VBScript or JavaScript or something that interactively allows the attacker to glean what the loaded memory locations are and then build a ROP chain dynamically based on that leaked address, it's possible. But like for static things like this, ASLR should break it. So let's look at this again. I see that I've got ASLR. And then I look at where VLC is loaded. Hex 400000, I forget how many zeros. Let me go back here. 0040, oh wait. So that address looks like it's in the VLC.exe app. Now, if I look at the ASLR column for VLC.exe, it says it's ASLR, which means that this address should be non-predictable. I've got an exploit here that is pointing to a location within that particular module. Well, I'm getting a little bit ahead of myself because I only started looking at this a little bit later. The first thing I tried doing is let's just try opening up the exploit. Does it work, right? Because sometimes people post stuff and it's just crap. It doesn't work. It's not well written. This machine has VLC installed on it. I basically ran poc.py. I can run it again. It basically generates an MKV file, which is like a video, Matroska video file. It's about 1 gigabyte in size, which I thought, like maybe the heap spraying is somehow related to it being able to work. Let's just try opening it. Let's say open with VLC. It'll spin for a bit, I think. If I look at the memory, right? Calc. This is the thing that causes vulnerability analysts to freak out. Even when you're actually just adding numbers on your desktop, if you see calc pop up, like it's this. Well, this actually worked pretty reliably. And if I look over here, nothing happened. So in this particular case, I'm running it through the wildcard machine because I don't know what it's going to do. If this is a Python file that I downloaded off of the internet, and I haven't actually analyzed the shellcode to ensure that it doesn't do anything like really bad. Now this guy says, in the comment here it says, well, exec shellcode for calc, but I don't trust it. I shouldn't trust anything I downloaded off the internet. Now, let's go in and let's run VLC, and let's go back to our Process Explorer again. And I can see right here, this address is the same. Anybody have any guesses as to why? I only figured this out as of this morning. So
it's not actually properly doing ASLR. That's my first guess.
Yeah. So when something says that it's ASLR compatible, there is a flag called, is that, wait, I don't know. Yeah. Let me go back to this particular one. This is the Visual C++ team blog, and they basically say you've got this flag called dynamic base. If I use the dynamic base linking flag, it will say I am now ASLR compatible, and it'll be randomized every time. If I go in here and let's run calc.exe, And let's go back to Process Explorer. Let's go ahead and find our calculator. I can see, well, let's see. First, you got to find the actual executable. I might not scroll through it because it's got a lot of stuff there. Oh, calculator.exe, right? So it does list ASLR, and I see this image base address that's like pretty random. If I go ahead and reboot my Windows system and I run this again, and I look at the memory location that it gets loaded, it'll be different. So that's my indication that ASLR is working. On the Windows platform, it's not like per execution of the program, but it's like at boot time, Windows does this thing where it shuffles the deck and it decides where things are going to go. What causes this to break exploits is if I have an exploit for calculator.exe, I can't do ROP on it anymore. Without a memory leak, without knowing where that module gets loaded, I can't say, please jump to this particular location. Let me edit this with idle again. I don't think I have to scroll too far, right? So this is a 64-bit, and they basically just decided right there, I'm going to go to this location. So I'm going to do a similar sort of example here. If I edit this particular document, I did this ahead of time. I could probably do it live, but basically, if I look for shellcode somewhere, oh yeah, right here. So what I basically did is that there's a whole blob of shellcode text, and because it's an exploit, it's very clearly marked as shellcode equals whatever. In this particular case, I just replaced it with a pair of CCs. So let's go ahead and try that. I basically just generated a separate file, and if I'm lucky, it'll launch WinDebug. I forget if in the snapshot I have it located, or if I have it set up to do just-in-time debugging. But this will allow us to kind of more interactively take a look if it pops in with the debugger. If it doesn't, I'll reinitialize the just-in-time. All right, cool. Unfortunately, the screen's a little small, but I'm kind of scrunched here. But I can see right here, I put in a pair of CCs. And the reason I did a pair is just what I mentioned before, because of byte alignment. If I only put in one CC, this would have ended up as like the second part of another instruction. So you put into probably 4 is a little bit safer. But what I can actually do is at this point, I can confirm. Wait. Yeah, let's go back to Windows Explorer here. Let's look at our exploit again. I'll edit this with idle. And then I'll get to the punchline at the end here. But I just wanted to show you a little bit of how you might be able to analyze a particular exploit. In this particular case, like here's the ROP gadgets. And this is telling me at this location there should be an exchange EAX ESP. If I want to, I can go in my debugger and say, well, just tell me what's at that location. Predictable code location. That is the bane of anybody trying to defend a system. If I have predictable code location, that means any of those applications that have predictable locations, I might be able to take something that I found through fuzzing, and I might be able to just actually produce a working exploit out of it. If I were to go back to my POC again, I can say, well, let's try another gadget here. This one should pop RCX and then return. Right. The reason they call it return-oriented programming is I'm basically finding specific memory locations that I go to that do the thing that I want. In this particular case, it will take whatever value is pointed to by the stack pointer, and it will load that value into the register, and then it does a return. They call it return-oriented programming because every gadget that I'm dealing with, it's a set of instructions. This is the smallest gadget I will ever have, where it's a single instruction and then a very simple return. If I have control of the stack pointer, Let me go over here. Well, this doesn't really tell me too much because it's all, well, I mean, it is kind of populated with some stuff. But basically, every time you run a return instruction, what it will do is it will increment to the next value that the stack is pointing to, and then it will execute code at that location. So basically, what you're able to do is chain together individual, what they call gadgets, to achieve what you want. In this particular case, they've decided, whoever wrote this exploit says, well, I do my stack pivot here. I pop something into RCX. My target address is some variable here that I have earlier. It pops something else into RDX. I unprotect my memory, and then I execute my shellcode. Let's just do it one more time to see if it counts. We'll open it with VLC. What I'm doing with this particular exploit is it's very similar to what I was doing with Office, but I'm interested in how reliable is this exploit. And I've got calc.exe. Like, anytime you have a reliable exploit, this is something that means the alarms need to be sounded. This is something that the attackers are going to jump on. I'll get to, anybody else have any idea? So if I look, oh wait, I've got to launch it again.
My next question is, how did said person stumble upon this?
How did they know, right? How did they know that it wasn't, well,
VLC, I mean, like, how do they know that VLC wasn't properly initiated as ASLR?
I'll tell you at least one thing.
Obviously more than the dynamic base that dictates ASLR.
Let me make sure I get my right thing processed here. How did the attacker know? Well, that's an interesting question. But it could be that they decided to look at a fuzzing result and they were able to run it once and it worked. And then they tried it on another machine and it worked. There's something special about this address. This address is used by every Windows application that's not randomized. The 40000, that's a magic address. If I ever see that address being used, I know it's an executable that's not being randomized. If it's a DLL, I think it's 10000. There's certain like heuristics for like something not being randomized. In this particular case, the attacker might not have known that ASLR was not in play, but it doesn't really matter because this is basically Mark Rusinovich. It's sysinternals like figured out, well, if it opts into dynamic base, it's randomized, and I'm just going to put that value in the column there. But if I'm looking, what really matters is what is the base address? The image base is what the image is suggesting it should be at. The base address is what it's actually loaded at. If I know that that's the same location every single time, I don't care about ASLR. It doesn't matter. Any guesses before I go to the conclusion? So if this says it's ASLR, why is it not being randomized? This is a problem, right? If I, as a defender, which I did until today, or yesterday, or whenever the hell I was looking at this, if I'm relying on this column to say, hey, everything's fine, everything's going to be okay, you don't need to worry about memory corruption issues as much because it's being randomized. Why would something indicate, at least in Process Explorer, there were other tools that I looked at too that also said, yeah, this will be randomized, but it's not. There's a tool you can use. This comes with Visual Studio. I was trying to think if there was, I tried to find if there was a standalone version of it that I could just run. And it's called dump bin. If I run dump bin, it'll tell me like there's some arguments I can run. If I run dump bin / headers, let's see if I remember. I copied the executable here. Let's look at the headers, right? And so dump bin is just telling you information about the PE headers. It's telling you information about what is this executable telling me that it is. If I look, let me use, I don't know if I have less on this or not. Let's try it. if I look right here, dynamic base, that's this flag, right? So these tools like system or process explorer from sysinternals, they look for this flag. Dynamic base means I, as the developer of my application, or at least the compiler or linker of this application, have claimed or that I would like to opt into ASLR, right? It turns out there's another flag that trumps this flag. And it is right here. There is an attribute of an executable called relocations stripped. Anybody know what the relocations table gives you? It's information about how executable code can be relocated to a different location other than what it wants to be loaded at. This is a problem. I have an executable file here that both opts into ASLR and then also set an option that is incompatible with ASLR. So what this means is this code cannot be randomized. I'm in contact with Mark Rasinovich from Microsoft, and he's going to be updating Process Explorer to reflect this. But basically, the tools that are checking for ASLR compatibility are not fully checking. They're only checking for dynamic base. They are not looking at relocation stripped. What I ended up doing is
that is an attribute of, is that like a setting in the file, or is that?
It's in the PE header of the file that is generated at link time. So when I compile a program, and when it links together my object code, what it will do is it will construct this PE header in a way that it tells Windows about like what the app is.
What is the purpose? What's the intended useful case where you're stripping the relocation?
There is none. There is none, and there is no
But they put it in PE header as like it. So
they are two independent flags.
Allocate space in a header for this flag to be there.
They are two different. There are. Right. All right. Let's rewind before there was ASLR. If I have a DLL, oh yeah, this is actually a very good question, right? Let me go back to my. I think we got time. If I look at this executable, it's always located at this particular location. If I were to happen to run two instances of VLC, how does that not cause a problem? If both instances of VLC want to be loaded at the same memory location, why is that not a problem in a modern OS? Right. From the perspective of every executable, it thinks that it has the entire memory space available. It's just called virtual memory. Not to be confused with like swap space and other stuff like that. But basically, from the perspective of the executable itself, it thinks that it has everything. So when I have two instances of VLC, they each think that they have the full memory space and they can load themselves at that same location just fine. Now, when it comes to DLLs, DLLs also give an address that they would like to be loaded at. But what if I have a program that uses two different DLLs from two different vendors that weren't in cahoots and weren't cooperating, and those DLLs try to get loaded at the same location? What happens? You have a collision, and what Windows does is it silently rebases the library to get loaded at a different location, right? So if I go back here to my terminal, this relocation table is something that existed even before ASLR was a thing. So this is its own independent setting of a PE file. Now, at some point in time, starting with Windows Vista, they implemented something called ASLR, which is like above and beyond relocation because it can apply towards the executables themselves. The reason that those two properties of a PE file aren't connected is because they were implemented at different times, and you
Because
can.
history matters.
History matters, right? Now, why would I ever, let's go back to my dump bin here. Why would I ever have an executable file that both has relocation stripped and also opts into ASLR? There is not a single Microsoft compiler or linker that will give you an executable that has those properties because they've realized you can't do that. This is an executable that was produced with a framework called MinGW, which uses like GCC, and it basically gives you the headers that you can compile something on Windows. So I actually took a virtual machine here, which is just an Ubuntu. My password is test, if anybody wants to know. Let me find my right terminal. Oh, Jesus, task switching in Linux. On any platform, it could be a Windows platform, it could be Linux, it could be FreeBSD. You can do this thing where you can cross-compile an application, and basically I can produce a Windows executable. This is kind of ridiculous, so I might just try to switch to a different window here. Yeah. It's eventually loading. I'm going to forget that I have the screen at all, and I'll tell you that it is possible to create a Windows executable on an Ubuntu or Linux or any sort of system. Use MinGW. I created a very simple Hello World application here. It started out as just one line. I'm not a C programmer. I don't know anything about coding in C. It scares me. So every program I write starts out with Hello World, and then I've wrapped it in a loop. But it turns out, I feel lucky that I have this on the screen while I'm waiting for it to do whatever. This is my code that I compiled. This is a program, and the first thing I did is I just did a Hello World, and I compiled it as an executable, and it runs. And I can copy it to a Windows machine, and I run it, and it just says Hello World, and it exits. So that was kind of neat, and it worked. You can create Windows code if you don't even have Windows, which is kind of neat. The problem is if I wanted to check if this code was randomized with ASLR or not, I need something that keeps running. Because if it just runs, displays its Hello World, and then it terminates, I can't open it in Process Explorer and look at what it's doing. So I just put a while loop around it, and it just, every second, it prints out Hello World. And it turns out, oh, good, my thing is a little bit responsive. Let's go, I think I have a directory here called MinGW. Let's go back to Windows 10, close this up. I'll copy in this thing called hello w32 loop.exe, and I'm just going to run it. Cool, like I can code. This is awesome. I've now created C code. It's kind of scary. I should not be doing any sort of C coding. But, what did I call it? Hello. Anybody see anything fancy about this particular code? Does that look familiar? It's the same thing that VLC loaded at. It is the default address that code gets loaded into. Now, what I did to create this is I just compiled it with MinGW. There's a tool, there's, let's see. Compile for Windows on Linux. This is what I used. That Hello World code, I did not write that code. I copied and pasted it. That's how everybody codes, right? Start out with that, copy it, and do it, right? And what this does is this shows you that I can now run this MinGW, and I can create this exe file for 32-bit, and I can create the exe file for 64-bit. I just did this. This is like, I'm a developer. I want to do the very simplest thing. I want to use MinGW because I don't have a Windows system, and I want to create an application. What this has done is this has created a binary that is not ASLR compatible, even though sysinternals Process Explorer thinks it's ASLR compatible. It is not.
So by default, somehow the MinGW does the dynamic base.
By default, MinGW applies the dynamic base flag, but it does not create a relocations table unless you do something. It's this line right here. What does this line do? I have no clue. But I think it indicates to my linker that, hey, I'm a DLL. Do the things that you would do for a DLL, which is I create a relocations table, because in order to be a DLL, I need to be able to handle a load collision, which causes it to be able to be relocated. So I actually compiled another version of this Hello World app with that particular line uncommented. The decal spec DLL export. Well, so let's go back to my Windows 10 VM. I'll get rid of this one. I don't like it. This one has DLL export. So let's drag that in.
It still sounds like an archaic option for the old style, the
Yeah.
ASLR code, right? So
Right.
This is really kind of a workaround.
It is a workaround. Well, let's look at hello W32 loop. It's the same code. If I look at this code right here, it's basically the same thing. All I did is say cdecal DLL export. And what do we got here? Something other than 40000. What this means is this code cannot be attacked with a trivial return-oriented programming attack because there's no predictable memory locations. If I was an attacker and I found a bug in my Hello World app and I wanted to write a memory corruption exploit for it, I would need to figure out where I need to go. If it's not randomized, I can just go there. I know exactly where it is. It's as if I was in the Windows XP days and I just hard code addresses in and it just works. In this particular case, I would need my exploit to be able to leak a memory address. So like something that would indicate that I'm loaded at B9 and then generate my ROP chain dynamically and then trigger the vol using the ROP chain that I've dynamically generated. It raises the bar significantly. What's the bottom line here? There is a bug. Do I have it open here? There is basically a bug. Let me see if I can pull up my Windows browser here.
Where did you? I mean, I guess you Googled some more Google food to find that like.
Well, it turns out it's a bug in binutils. This is a bug in like the GNU binutils like toolkit that like generates code. And back in 2014, somebody said, hey, you know, this is a Tor developer. They said, yeah, it'd be cool if you added an option that allowed you to enable the relocation table. They never committed it because they wanted a couple things, and it basically has been sitting idle for 4 years. Here's Daniel Verkamp in 2013, and he's like, you know, it's cool that you're using dynamic base, but it's kind of shitty that you're stripping the relocation table. And then here in June of 2013, here, June 2013, somebody says, very interesting. Kai, any comments? And then a couple months or a month later, the guy's like, hey, just a general reminder, this would be kind of cool to fix. And it's been sitting idle since 2013. Now,
So the VLC guy code in Linux using MinGW, and that's why.
VLC is building their Windows executable using MinGW. VLC has basically decided to work around the bug by adding this single line. He's already got a patch in paste bin, and he adds a bunch of comments, and it's a one-line fix. Now, that general conclusion here is bin utils should fix their code because you shouldn't be relying on the developer to know that they need to either add a special command line to opt into adding a relocation table or know that they need to add this decal spec DLL export line. So in the end, bin utils should by default create relocatable code, but it doesn't.
So bin utils really,
They need to fix their code.
well, they haven't fully implemented ASLR support.
Correct.
They have
They've
partially-
said, yes, I'm ASLR compatible,
they
but they're
partially-
not.
Partially implemented
Correct.
ASLR.
It's
So
been
is
it's been this way for 5 years.
Right.
I will be putting together a blog post to describe this issue, and I'm going to synchronize it with the release of VLC. I think they're going to release it within a week. Now, had
that's a
VLC,
vulnerability by itself.
it is a vulnerability by itself.
Because you gotta. I mean,
Anybody who has used MinGW to create code on Windows is at risk. The reason this VLC exploit worked 100% of the time is because they didn't randomize their code. It wasn't through negligence of the VLC developers. It was that they were using a tool chain that produced code that just doesn't make sense because you have two flags that contradict each other. You've got one flag that says, I would love to be randomized, and then you have the other attribute of the library that says, there's no way in hell you can randomize me. What makes this problem a little bit worse is that Process Explorer, they are deceptive in what they're telling you. As a person who cares about the security of my system, I often will look at my system and see, show me the things that don't use ASLR. Oh, this is running without admin privileges. That's why some of these are blank. But if I look at VLC and I see ASLR there, that makes me happy.
So how
What
many-
makes me very unhappy is that's lying to me.
How many bugs do you think you now missed because of the false output of the tool?
So I will say I have done fuzzing campaigns where I'll look at something and I'll find an interesting crash, and then I look at the code and I'm like, well, it all uses ASLR. I'm not going to bother. I don't know if I've necessarily looked at the loaded address to see does it actually load at a fixed address every single time. So
And you're saying only on reboot does that fixed address change. So if you
Correct.
program open again, ASLR.
yeah, you have to reboot. You would have to reboot, but if you see anything other than 4.0 whatever.
You can assume it's.
So actually, what I ended up doing is I created a tool. Let's go to, and I think this will put us right at the end of time. Oh, geez. This is when I was looking at RTFs. Get rid of this. Let's try it. Check ASLR. I'm not going to scan the whole system, but I'll just scan that directory. This gives me a list of every executable or DLL, but it's generally only executables because DLLs, I think by their nature, they have to have a relocation table. This is a script, check ASLR. I can run it on any system and it'll tell me every executable on my current system. I think that was maybe the end of or no, that sounds like chat. Anyway, this script, I can run it on any system and it'll tell me what programs, I swear. Somebody really wants to chat. This script, when I execute it on any system, I can point it at a directory and it will tell me every executable that is implying that it's ASLR compatible, but actually is not. I don't have a lot of code on my system, but I found that like I had FFmpeg, I had Hashcat, John the Ripper. I think those all were like things that implied that they were ASLR compatible, but are not. FFmpeg on Windows is pretty cool because FFmpeg has a huge attack surface. And if I know that the FFmpeg binary is not being randomized, then I can write an exploit for it. Pretty easy. So this script is available. I'm basically going to be putting together a blog post that kind of talks about binutils has a problem. Because of this problem in binutils, VLC is the victim of it. There is a public exploit for VLC 2.2.8 that allows people to achieve code execution reliably. And the reason that that works reliably is because binutils, this particular bug, it's in binutils.
Right.
It's known. Now, this particular person said, well, you should add another optional command line flag. I don't think that's the right solution because that still puts you in the state where by default you're generating less secure code. And I don't know if that was necessarily why they didn't implement it, but so they said that they would happy to be accepted, but nobody ever followed up again. If I can draw more attention to this existing bug, then that would be a win. I might try to reach out. Well, this is open source, so it's one of these things where, but I think the general idea here is this is a known bug. The consequences of this known bug were maybe not fully appreciated in 2014, but I think the example of VLC being a victim of this bug this is why this matters. If this bug were fixed, if this bug would have been fixed after they filed it, VLC would not have had a working exploit. That's a huge difference. It makes the difference between reliable exploit and no exploit. The crash still would have been there, but it wouldn't have been something that you can just double click on a MKV file and end up with code execution with. So anyway, that's it. I'm gonna